Hey Fizz kids, Mr. C here, and we're going to talk about Newton's third law today. This is sort of the last law of motion that we're going to talk about in this class, and it's a pretty cool one. And it's really one that's very applicable to everyday life. So Newton's third law basically states that every action force, for every action, there must be an equal and opposite reaction. And all it means is that it's equal in magnitude, equal in magnitude, and opposite in direction. So the action and reaction forces act on the exact same object. So in this case, we have the guy here. And we know that the force of the floor is pushing up on the man. So that's like typically what we think of as the normal force. However, the man is also pushing down on the floor, and that would be the reaction force. So these kind of go together. So we have like the force of the man on the floor and the force of the floor on the man. In this case, we have F1 and we have F2. So we have the force of, our box pushing down on the table, but we also have the force of the table pushing up on the box. And we write this as force 1 is equal to negative force 2. So basically, we have the same magnitude and opposite direction. That's why one of them has the negative sign. The negative sign here basically just means we have opposite direction. Pretty awesome. Once again, here's just another example. We have the force of the hammer on the nail and the force of the nail on the hammer. What's important to remember, though, is that whenever we draw our free body diagram, we don't ever include the two forces, so the action and reaction pairs, because they're really, like, if we're studying the nail, we're going to look at the force of the hammer on the nail, and that would be our force right there. We wouldn't do that other force of the nail on the hammer. But if we wanted to, say, study the hammer, we would look at it and we draw, okay, well, we have the force of the nail on the hammer that's pointing the opposite direction, but they should never show up in the same force body diagram. So that's very important. Never really happen, mainly because they happen on two different objects. One thing about how this sort of applies to motion, this whole thing, is that in order for us to walk, we have to have friction. If there was no friction on the floor, we basically would just kind of look like some old-fashioned cartoon where we're running and our legs are spinning and we're not going anywhere. We have to have that friction to do. And what happens when we walk is our foot sort of pushes back on the floor of that surface. So that's what this arrow is here. We're pushing back on the surface. The reaction pair that allows us to actually move forward is friction, which is pushing forward. It points opposite in the direction of the other force. Pretty cool. Tires work in the exact same way, and because we're not moving, because we're not slipping, our foot's not slipping, it's standing still. It's holding on to that same point on the surface. We're just going to call that the static friction. You don't really need to know that right now. We're going to talk more about static friction later. But force that we apply on the surface and that static friction of the surface on us is an action-reaction pair that allows us to walk forward. That's why whenever you're ice skating, it can be really hard to walk because you're just standing there and there's really no friction on the ice, and you'll just sort of be, try and walk and your foot just slips back and you don't go anywhere because there's not that reaction that you need to move forward. Pretty awesome. So another weird way to think about this is, let's say we were studying an apple falling down from a tree. The action is that the earth is pulling down on the apple. So that's one that we typically look at. It's like that force of gravity. The reaction is that the apple also pulls up on the earth, which is weird to think about that because you're like, well, the earth pulls down the apple. That's why the apple falls to the earth. But the earth doesn't move toward the apple. This isn't exactly true. It does move toward the apple, but we're going to look at that motion in a second. Based on Newton's third law, we know that that force of the apple has to be equal to the negative or the opposite direction of the force on the earth. So like if this is our apple here, the earth is pulling down on the apple, but the apple is pulling up on the earth. And these forces are equal in magnitude. But remember, force is equal to mass times acceleration. Let's just work out some numbers. So let's just say we know that the force of the apple, that force of gravity, is equal to 1.96 newtons. right? That's pretty simple to do. We just have our 200-gram apple times by 9.81 meters per second, and that's the force of the Earth on the apple. So force of Earth on apple, that's equal to 1.96 newtons. Based upon Newton's third law, though, we know that every force has an equal and opposite reaction or opposite force. In this case, we know that the force of the apple is equal to negative the force of the Earth. And we know that the force of the Earth is equal to mass times acceleration. The only difference is this mass is the mass of the Earth, not the mass of the apple. If we plug in those numbers, we can solve for what the acceleration of the Earth is, and we actually find that the acceleration of the Earth is 3.28 times 10 to the negative 25 meters per second squared. That's a very, 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 very tiny acceleration. We actually can't even measure that. And that's where this whole action-reaction pair gets tricky. Even though they have the same magnitude of force in an opposite direction, that doesn't mean that the motion has to be the same. The accelerations are often going to be different because our objects will have different masses, and because of that, like in this example here, the force of the Earth on the apple is equal to the force of the apple on the Earth, but the accelerations caused by those forces are very different because the mass of an apple is so much smaller than the mass of the Earth. Let's do a quick little question. While driving down the road, an unfortunate bug strikes the windshield of a bus. Quite obviously, this is a case of Newton's third law of motion. The bug hits the windshield and the windshield hits the bug. That poor, poor bug, although it probably deserved to die. I don't like bugs. Which of the two forces is greater, the force of the bug or the force of the bus? So is it the force that the bug feels from the bus or the force that the bus feels from the bug? Go ahead and take a moment to answer that and see what they are. Well, if you answered 3, they are equal, you are correct. Newton's third law tells us that they're equal and opposite. So in this case, the magnitude of each of these forces is going to be the exact same. They're going to be equal. The only difference is that they will be opposite in direction. You may ask yourself, though, if these forces are equal, why does the bug get splattered all over the place and die? Whereas when you're in a car, you probably don't even notice when you hit the bug most of the time, unless it was a really big one and you hear like a splat. Most of the time, you don't realize you hit the bug. Why is this? Well, let's see. So we have our bug, and we have the force of the bug on, we might have a force of gravity. And, we have some sort of force that's pushing us up because we're flapping our wings. And then we hit the bus, and bam, we have the force of the bus on the bug. For the bus windshield, however, we have the force of the bug on the bus. So those are kind of our two forces here. We know that earlier that the forces are equal. So F, we're just going to call this A and B. So we know that FA is equal to minus FB. And we can see that here, where they have the same magnitude and they're pointing in opposite directions. In this case, we're pointing over to the left, and in our bug case, we're pointing to the right. So what's actually happening? Well, in the case of the bug, the mass of our bug is incredibly tiny. And because of that, it has a massive, massive, massive acceleration, or in this case, a deceleration. It slows down almost instantly, it's so big. On the other hand, the mass of the bus windshield and the bus itself is huge. And because of that, it's going to experience a very small acceleration because we know that our force here has to be equal to our force here. Pretty cool, right? Because the mass of the bus is so big, it's going to experience a small acceleration. We just look at this here. Let's say we have our force is 2 newtons. The mass of our bug is 0.01 kilograms, and our mass of our bus is 1,000 kilograms. Our bug is going to experience that acceleration of 200 meters per second squared. The bus, though, is only going to experience 0.002 meters per second squared for its acceleration. And because of that, you're not really going to feel that small of an acceleration. That's why you don't notice whenever you slam into those bugs going at such high speeds. However, the force exerted on the bus by the bug and the force exerted by the bus on the bug is going to be the same because of Newton's third law. Yay! Okay, so now go ahead and I want you to answer the video check for video 3 in Google Forms, and we will talk more about Newton's third law in class. I will see you all tomorrow.